Hi, welcome back to Classical Mechanics by Unify Physics. Let's today discuss velocity dependent potentials and dissipation function. In fact, we'll discuss only the velocity dependent potential part today, and in the next session we'll discuss the dissipation function. So we'll look at the important problem where we have a velocity dependent potential, and actually we are looking at only this particular issue because it's a very important issue. It's a system consisting of a charged particle in an electromagnetic field. It's a very important problem for various reasons, okay, even in theoretical, and we'll see an important aspect or an important property of this kind of a system, which is known as the gauge transformation and gauge invariance. Okay, there's an important property called gauge invariance, and we'll discuss a couple of examples. Okay. So normally we said that, so we started by saying that we got the Lagrange's equation in this form. If you remember the D'Alembert's principle, from D'Alembert's principle we got the Lagrange's equation in this form, d by dt of dou t by dou qj dot minus dou t by dou qj is equal to qj, where we called this as the generalized force, components of the generalized force. Okay. Now, if we substitute, if this force can be derived from a potential, we said that we can write it as what is a derivative of gradient of a potential, and then we can combine this, okay, with t minus v, with L equal to t minus v to get it into this form. All right. So here we had an important condition that the forces or the generalized forces have to be derivable from a potential. Okay. In particular, you should be able to get the force in this form basically, okay, dou v by dou x or minus dou v by dou x, like that. All right. So we needed to have these forces as gradients of potentials. All right. So here we are going to show that we can again write the Lagrange's equation in this form, or the Euler-Lagrange's equation in this form, even if the potential is velocity dependent. All right. But not all velocity dependent potentials allow you to write your equations of motion in this form. We need to have velocity dependent potential in such a way that the forces can be derived or the forces can be written like this, okay, which involves the usual gradient dou u by dou qj, the derivative, okay, and then d by dt of dou u by dou qj, right. So you can see this here. Now if you substitute this thing, okay, suppose your forces can be derived from the potential, from the velocity dependent potential in this form. Okay. Now normally we said that our velocity dependent potential should be, you should be able to write it as, the generalized force you should be able to write as minus dou u by dou qj, then we can combine it into this form. All right. Now we are saying that we can combine it, okay, or we can write the equations of motion in this form, in the form that we know and love. Okay, we can write it in this form if the generalized forces can has an extra term of this form, okay, d by dt of dou u by dou qj dot. I mean, that's easy to see. So instead of qj here, you substitute, this term, you get minus dou u by dou qj plus d by dt of dou u by dou qj dot. Okay, we see that it nicely combines here. All right, this dou u by dou qj here, you can combine it with this, okay, and you can write as t minus u, okay, t minus u. Right, here we can combine these two terms and write t minus u, and you see that this part is written exactly in a way that we can combine this term also. So it also can be written as t minus u, okay, because we have got a d by dt here, d by dt here. If you take to this side of the equation, we simply have dou by dou qj dot of t minus u. Right. So we are saying that if the generalized forces can be written in this form for a velocity dependent potential, we can retain this form of the Lagrange's equation with L equal to t minus u. Okay. So this is a very special case, and we are interested, or the only problem that we will be discussing in this manner is the charged particle in an electromagnetic field. Okay. So this u, we may call it as the generalized potential, okay, or it's usually called the velocity dependent potential. Okay. And the application, as I said, is a very important problem called the electromagnetic forces acting on moving charges. All right. Okay. So the equation of motion, for example, for a charged particle in an electromagnetic field is given by this Lorentz force law. Okay, you can get the equation of motion from the Lorentz force law. right, which is F vector is equal to Q E vector plus V vector cross B vector. E is the electromagnetic field and is the electric field and B is the magnetic field. Okay, so you are familiar with this is called as the Lorentz force law. Okay, now in principle, if you are using the Newton's formalism, we can always write m d square x by dt square, or what do you say, f equal to ma. All right, so this f is equal to ma vector differential equation. Solve it and study that. We are not doing that here. We are using the Lagrangian formulation. All right, so you might already know that this is the relevant equation that gives you the force acting on the system, which determines the time evolution of the system. I say that this determines the time evolution of the system because Newton's law says that f vector is equal to m d square x by dt square. All right, so if you know this force, if you know the exact expression for force, you can write this equation, and in principle you can solve this differential equation to get x of t and let's say p of t, all right, or v of t, whichever way you decide to define the state of the system. Okay, all right. So that's what we do. Now the question that we have here is, can we get the force law? All right, f vector is equal to m d square x by dt square. Okay, or we can write mx double dot. This mx double dot is equal to f vector, where f vector is this. All right. Now the question is there a Lagrangian that leads to this equation? All right, for a charged particle in an electromagnetic field. All right, so can we construct a Lagrangian that leads to this particular equation? That's the question. I hope that's clear. The question is, can we construct a Lagrangian, or is there a Lagrangian that gives rise to this particular equation of motion? That's the question. All right, the answer is yes, there is a Lagrangian. Okay, or there's a potential. Let's say there's a velocity dependent potential from which we can construct a Lagrangian. All right, so for this we need to familiarize ourselves with the concepts of a scalar potential and a vector potential. All right, we have got a scalar potential and a vector potential. So you might already have known that the electric field can be written in terms of the potential in this form. Okay, and the magnetic field is written as the what is a cross product del cross A. It's not exactly, so this is actually an operation. All right, it's an operator acting on A vector. All right. Okay, so these equations you might be familiar with. All right, and these scalar and vector potentials. All right, the scalar potential and vector potential, we can it's convenient to write the electric and magnetic field in terms of the scalar and vector potential. All right. Now for later reference, it is useful to know that these things are not completely separate things. All right, we can always write these as a components of a 4 vector. If you like, we can write a 4 vector known as a 4 vector potential with components. Okay, these are 4 vectors. We'll look at 4 vectors later on, but this is a convenient way to keep some things in your mind. All right, 4 vector means, by 4 vector what I mean is that a 4 vector obviously has 4 components. We say it has a time component which we denote as A0 and 3 space components which we can simply write as A vector. Okay, so in this case, this is what you mean by a 4 vector. It has 4 components because it lives in the space time. Okay, you say the Minkowski space. All right, so A mu A0 comma A vector. You can also write this as, okay, so in this case we know that, all right, we know that this scalar potential and vector potential act as components of a 4 vector if you write them like this. Okay, A mu is equal to, okay, the components are phi divided by c and A vector. It's quite easy to remember. Okay, this is a very convenient thing to remember. There is a 4 vector potential of which the components are the 0th component or the temporal component. The 0th component is just phi by c, which is scalar potential, divided by constant of light c, and then the space part. Okay, this part is known as the space part of a 4 vector. These are just A vector. Okay. Now, this C, it may be a bit difficult to keep track of. See, that's why theoreticians usually work with the unit system where C equal to 1. Right? But it's convenient to remember that in SI units, this is the way we write the 4 vector potential. Okay, so it's a good thing to remember that this phi and A are not completely separate objects. Okay? These are components of a 4 vector. Okay? We'll discuss 4 vectors in more detail when we go into special theory of relativity. but sometimes, all right, this particular information might help you remember some things. Okay? This is a nice unifying thing, this relativity, and it might be helpful to remember some things. Now, if you find it difficult right now, before going to special theory of relativity, you might find difficult, then just leave it, all right? That's just an extra piece of information. All right. So, the point here is that electric field and magnetic field, they can be written in terms of the scalar potential and the vector potential. Okay, you remember this, E vector is equal to minus del vector phi minus dou A vector by dou t, and B vector is equal to del vector cross A vector. All right, and there is a potential from which the force can be derived. Okay, and the velocity dependent potential is given by U is equal to Q phi minus Q A vector dot V vector. Okay, so as we said earlier, okay, the Lagrangian can be written as T minus V, L equal to half mv square T minus U. All right, it's half mv square minus Q phi plus Q A vector dot V vector. Okay, now at first sight, okay, there are other ways to motivate this particular Lagrangian. All right, there are other ways to argue that this is the particular, this is the Lagrangian that gives rise to the Lorentz force law. Right, but we don't go into such details because this Lagrangian, you have to remember, you have to keep it in mind. It's an important Lagrangian. All right, you will use it to solve problems. Okay, now one way to define the Lagrangian, all right, one way to define the Lagrangian, I don't go into the mathematical details of or other ways to motivate this particular Lagrangian. The important thing here is that the one definition for Lagrangian, what's the Lagrangian? What's the Lagrangian? Okay, we can say that Lagrangian, okay, one simple definition. Okay, this is a general definition. This T minus V, T minus U, these are not general definitions, all right. The Lagrangian cannot always be written as T minus U or T minus V. In our syllabus, we mostly deal only with Lagrangians which can be written in the form kinetic energy minus potential energy, but don't get fooled by this. Not all Lagrangians can be written in this form, T minus V or T minus U. Okay. These are actually only a small class of problems with which we deal mostly in the MSc syllabus. All right, you have to keep in mind that this is not always the case. So, what's a Lagrangian? Well, what's Lagrangian? One way to define Lagrangian is this. Okay, we can say that Lagrangian is that function, okay, or Lagrangian is a function, okay, such that, we don't go into the details, such that d by dt of dou L by dou Qj dot minus dou L by dou Qj is equal to 0 constitute the equations of motion. All right. So, what's a Lagrangian? Lagrangian is that function, okay, which gives you the equation of motion if written like this. Okay, that's the definition for Lagrangian. All right. So, the question here is, what's the Lagrangian that gives you the Lorentz force law? What's the Lagrangian that gives you the Lorentz force law? And the answer is, this is that Lagrangian. All right, this is the Lagrangian that gives the Lorentz force law. Now, it's not sufficient to just claim this. We can actually show that this gives rise to the Lorentz force law. That's what we are going to do next. Okay. Now, in the previous NET CSIR exams, there have been problems based on this part. Okay, it may not exactly be the problems that we do here, but very good idea about this particular Lagrangian and the ways we work with this Lagrangian. All right, it's important. You need practice in this aspect. Sometimes they may ask about the gauge transforms. Sometimes they ask something conceptual based on the fact that this is a velocity dependent potential. So it's a good thing to practice with this thing. All right. Also, in the history of theoretical physics, this particular Lagrangian and this particular potential and the Lagrangian of this form, the property of gauge invariance that we'll talk about a bit later, these are very important. All right, even if you go to particle physics or quantum field theory, this particular fact that this potential or this what do you say, this potential has a property called the gauge transformation invariance. We'll come to that. Okay, it's very important. Right. So, that's the reason why questions associated with this thing appears often in the competitive examinations. Right. So, that apart, now let's see the equations of motion. Now, the question is this: suppose this is the Lagrange's equation. Right. Suppose this is the Lagrangian given to you. What are the equations of motion? So the question, okay, you can consider it as a problem. The problem that we are going to solve is this. So this we can take it as a problem and do it. Okay. Now suppose this is the Lagrangian. Alright, you don't know anything else, forget everything else. The Lagrangian is given. Okay, Lagrangian is given. What are the equations of motion? We know what are the equations of motion. This Lagrangian is constructed in such a way that we get the Lorentz force law. Okay, but we have to check. Alright, that's a problem here. Lagrangian is given. What is the equation of motion? Alright, so let's do this systematically. We can write the Lagrangian in this form: L equal to half m x dot square plus y dot square plus z dot square, okay, minus q phi. Why do I write x dot square plus y dot square plus z dot square? Because that's v square basically. It's v vector dot v vector, and it's x dot square plus y dot square plus z dot square minus q phi plus q a vector dot v vector. I will write as ax x dot plus ay y dot plus az z dot. Okay, that's Lagrangian. Right. Now actually you know how to do the rest of the problem. You are very familiar with these things. We need to find dou L by dou x dot. What's dou L by dou x dot? Immediately we get an mx dot from here. So let's do it only for the x component. The rest follow exactly in the same manner. So this is mx dot. And is there any other x dot here? Yeah, there's an x dot here. Don't forget that. So that's plus q ax plus q ax. All right. Now one thing I want you to remember is that this is also the conjugate momentum conjugate to the coordinate x. All right. So usually the momentum conjugate we write as mx dot, but in the case of an electromagnetic field, when the charge is in an electromagnetic field, or when a charged particle is in an electromagnetic field, then this is the conjugate moment. Okay, this is what we legitimately call the momentum. There's also a contribution mx dot plus q ax. Okay, it's an important thing to remember. So this is mx dot plus qax is the conjugate momentum. Okay, such questions also can be asked. What's the conjugate momentum for a given Lagrangian? And you have to be careful when the potential is velocity dependent. All right. Okay, fine. What's dou L by dou x? What's dou L by dou x? So here there is no contribution. From here there is no contribution. From here, of course, we get a contribution. That's minus q dou phi by dou x. Okay, dou L by dou x. Okay, and also from here, okay, so you can write this as q. You have to remember that what we are talking about here is a vector field. Okay, vector field means associated with every point in space you have got a vector, which means basically that these components ax, ay and az, these components are generally functions of space and time. Okay, what you have to remember is that generally there's space-time dependence sitting here. A y of x comma y comma z, a z of x comma y comma z. Right? So when you take this derivative, you shouldn't forget this fact. So you have got dou L by dou x minus q dou phi by dou x plus q. You have got dou ax by dou x, x dot indeed. Okay, plus. Okay, I think I'll take this q outside, plus dou ay by dou, I think need more space. So this is dou L by dou x dot, and now let's write dou L by dou x dot, dou L by dou x over here. Okay, just to save the space, dou L by dou x equal to, you have got a minus q dou phi by dou x over the, okay, all right. So maybe it's convenient to pull this. Okay, let's write it separately. Plus, okay, as I said, you have to remember that this ax, ay and az depend on x, y and z generally. So when you take the derivative, you have to include all those terms. So you have got a dou ax by dou x, x dot. Okay, of course there's a q sitting here, so let's put it in this form, plus dou ay by dou x, y dot, plus dou az by dou x, z dot. Okay, so that's dou L by dou x. All right. Okay, now what's the equation of motion? The equation of motion can be written as d by dt. I'm just filling in the blanks here. Okay, d by dt of dou L by dou x dot is equal to dou L by dou x. That's equation of motion. Okay, so you take the time derivative of this thing and you get an mx double dot. Okay, so what do we have there? So if you construct this, you get d by dt of dou L by dou x dot is mx double dot, okay, plus q dax by dt. Okay, taking the time derivative there. This is equal to dou L by dou x. We already found our dou L by dou x here, and that's equal to minus q dou phi by dou x plus q. I think we can write this term as this whole term. Okay, we have got dou ax by dou x, dou ay by dou x, and dou az by dou x here. Okay, so yeah, let's just keep it like that. So that's minus q dou phi by dou x plus, okay, this is the left hand side, and on the right hand side we have got this thing plus q. Okay, this x dot is basically vx dou ax by dou x plus vy dou ax by dou ay by dou x plus vz dou az by dou x. Okay, this is our equation of motion. Now you just rearrange it a little bit. You see that mx double dot, you put it on this side, take this to the other side. You are just rearranging. Okay, so you get mx double dot is equal to q vx dou ax by dou x plus vy dou ay by dou x plus vz dou az by dou x, which is basically this term, and this term appearing here. You can pull this q outside. Okay, this term reaches here. Okay, if you pull this q outside, so it's equal to minus q dou phi by dou x plus dax by dt. We got it. Okay, that's our equation of motion. Okay, that's not all. This doesn't look very much like the Lorentz force law yet, so we'll try to rearrange. We'll try to do a little bit more manipulations. All right, what other things can we do? Okay? So let's look at this dax by dt. Let's look at this dax by dt. What's dax by dt? Okay, there's this rule. We can maybe write. Okay, dax by dt is equal to, you have got the what is the partial derivative with respect to t because of the explicit time dependence. Okay, this is dou ax by dou t plus, okay, so let's check what's this vx, because okay, I'll write it down here. What's dax by dt? Okay, first you have to take care of the partial derivative because of explicit dependence, but that's not all. There may also be an implicit dependence, which means that there will the ax can depend on time through the dependence of x, y, and z on time. All right, so to take into account the implicit dependence, we have to write dou ax by dou x x dot or dx by dt plus dou ay by dou ax by dou y y dot plus dou ax by dou z z dot. That's what I have written here. Okay, so dax by dt is dou x by dou t plus vx dou ax by dou x plus vy dou axy dou y plus vz dou ax by dou z. I hope you understand how it has come there. Okay, now one thing you can keep in mind is this. Now this looks like a scalar product of two vectors. Okay, one vector with components vx, vy, and vz. This is simply v vector. Okay, another vector with components dou ax by dou x, dou axy dou y, and dou ax by dou z. What's that? This is simply del vector ax. Okay, so this you can write as dou ax by dou t plus v vector dot del ax. Okay, that's what we have done here. Okay, so remember this general result. If you have some function of space and time x, y, z, okay, df by dt can be written as dou f by dou t plus v vector dot del vector f. This is a general result. You can make use of this in problems. Okay, so without going into all these details, if you look at this, you can immediately write this down. Okay, that's fine. Sometimes it may be useful to remember such things. Okay. All right, what do we have here? So we have just expanded this term. Okay, we have just expanded this term, and there's a minus q there. So you see that this term. So when we compare these terms, what do we have? We see that this term exactly cancels with this, okay, because there's a minus sign. So these terms cancel. I'm just combining them. Okay, and what else do we have now? Let's write it down. Mx double dot is equal to, already you have got a minus q dou phi by dou x over there. Okay, and this term also comes out, so you can write as minus q dou phi by dou x, or minus q dou phi by dou x minus dou ax by dou t. Okay, it's just this term. We have separated out this term from dAx by dt, and there's also a q there. Okay, what are the other terms? As I said, these two terms get cancelled. What do we have left there? There's a q sitting everywhere, so I'll pull it totally outside, and there's a vy there, vy dou ay by dou x. Okay, and correspondingly, since there's minus sign here also, it's minus dou ax by dou y. Fine. Okay, and there's a vz here, there's a vz also here. Okay, and there's a minus sign in between, so that is dou az by dou x, dou az by dou x minus dou ax by dou z. That's our equation of motion. That's our equation of motion. So let's just write it down here. Okay, what we have here is the equation of motion that we got is mx double dot is equal to, okay, just for future reference, mx double dot is equal to, we saw that there was a minus q dou phi by dou x minus dou ax by dou t. Okay, fine. And what are the other terms we have? We have got plus q multiplied by, you've got a vy here, okay, and okay, sorry, I'll write it down. Okay, vy, and what else do we have? Vy multiplied dou ay by dou x minus dou ax by dou y. Okay, that's dou ay by dou x minus dou ax by dou y. Am I right? Okay, and then we have got plus vz multiplied by, okay, it's dou az by dou x minus dou ax by dou z. Okay, dou az by dou x minus dou ax by dou z, dou ax by dou z. So let it be there. Okay, so that we can look at it. Okay. Now, if you are familiar with these kinds of things, you will see that this is very familiar with some sort of a cross product. Okay, so because there's this minus sign and y and x get interchanged, this is actually cross product. So what cross product is that? Okay, we can show that this is actually a part of this. Okay, apart from this q, it's actually v cross b. It's actually v cross b, because if you check, if you are careful enough to check v cross b, we are talking about the x component. Okay, x component. Let's look at the x component of v cross b. Okay. So you can write this thing usually, you usually write this determinant if you are familiar with this, and I, j, k or x, k, and then the components of the vectors here which involved in the cross product, and then you do that. Okay, but in the end, because of this antisymmetry property of the determinant, you will see that this can easily be remembered in this form, v cross b x. Okay, we are talking about an x here, so on the right hand side you will only have y and z. Y and z, okay, and only in such a way that they appear in a cyclic permutation. So v cos b x component is actually vy bz, and there will be another term vz by. Okay, and you look at the sign. XYZ is an even permutation. All right, you look at this. XYZ, YZX, and ZXY are called as even permutations. Other combinations are known as odd permutations. All right, so we have got XYZ here. Okay, this is just method to remember. Okay, you have to be careful always. Or you could do it with the Levi-Civita symbol. Okay, if you are familiar with that sort of thing. XYZ. So we have got XYZ here, we'll put a plus here. We have got XZY here, so we put a minus sign there. Okay, I'll do only one term here. And what's this BZ? What's this BZ? Okay. Let's check this BZ again. We know that B vector or BZ, we know that B vector is del cross A by definition. Okay, that means that BZ is actually Z component of del cross A. Okay, similarly you will also find for by. Okay, I'm not going to do that here. All right. Okay, what's this Bz? Bz is the z component of del cross A. What's the z component of del cross A? Again, do the same thing as I said. This is equal to, you have got a del, you can be careful because this is an operator, but it's possible to generalize this. So you will have a, already you have got a z here, that's one way to remember. So you'll have a del x ay and a del y a x. Okay, now you have to fix the sign here. What signs do we have? Okay, it's zxy. Okay, zxy is an even combination, so you have got a plus here and a minus there. That's an odd combination. All right, what do you mean by del x? It's x component of the operator del vector, which is dou by dou x. So this is dou ay by dou x minus dou ax by dou y, which is exactly this, dou ay by dou x minus dou ax by dou y. Okay. So we see that v cross b, the x component, is vy dou ay by dou x minus dou ax by dou y plus vz. You can also check for this one. Okay, you check for also this term by. Okay, you see that by, this term sitting here is minus by. You will see that this is equal to minus by, which means that this is equal to minus del cross A, the y component of del cross A. You can see that this is true. You can check it. Okay, you do that at home, or you can practice on such things. Okay, you'll get the thing. So what we see here is actually what do you say? What you see here, this total term is actually v cross b, the x component of v cross b that we have shown right now. Okay, so the total equation of motion becomes mx double dot is equal to q. What is this now? You already know that this is actually the x component of the electric field. Why? Because E vector is defined as dou phi by, minus del vector phi. You also have a q minus q del vector phi minus dou A vector by dou t. We have seen this thing. So if you take the x component, it's just minus q dou phi by dou x minus dou ax by dou t. That's exactly what we have here. So this term we can write as ex, and this is simply v cross b. You pull out this q from everywhere. Okay, sorry, there's no q here. I'm sorry. So this is E vector equal to minus, we can just check. Okay, we already had written it down. So E vector is equal to minus del phi minus dou A vector by dou t. So you can pull this q out here, and this term can be written as, did I miss a q here? Yes, I missed a q there. It's all right. So this becomes mx double dot equal to q. This is ex, and this is v cross b x component. Okay, it's exactly the Lorentz force law. So we have shown that the Lagrangian that gives you the Lorentz force law is this. Okay, the Lagrangian that gives the Lorentz force law is exactly this. Okay, and again, by what do you mean by Lagrangian? Okay, what do you mean by a Lagrangian? A Lagrangian, you can call the Lagrangian, it's a function. It's a scalar function. It's a function constructed in such a way that it's a function which is constructed in such a way that it gives rise to the Euler-Lagrange equation. Okay, that's one way of. Okay, we'll be more precise. Did I say this before? Okay, just let me be careful here. Maybe I'm repeating myself. It's all right. Okay, what do we mean by Lagrangian? All right. So what do we mean by a Lagrangian? All right. So far we have seen that L equal to t minus v. Okay, and in this special case it's t minus u. Okay. So you have to remember that the systems for which you can actually write L equal to t minus v or t minus u are actually very few. Okay, although in the MSc level we study mostly such systems. There are exceptions that we will be seeing, especially in the relativistic particle, etc. But generally, this is not the correct definition for L. Okay, it so happens that for many systems, the Lagrangian happens to be in the form t minus v, right? But that's not always true. So then, how do you define a Lagrangian? How do you define a Lagrangian? Okay, so one way to define a Lagrangian is this: Lagrangian is that function. Okay, is a function such that d by dt of dou L by dou x dot minus dou L by dou x equal to 0 is the equation of motion. Okay, so what's the definition for a Lagrangian? Lagrangian is that function which, when combined in this form, gives you the equation of motion or the time evolution of the system. Okay, that's the correct definition for Lagrangian. And here what we have shown is that the correct Lagrangian that gives rise to the equations of motion for a charged particle in an electric field is actually this thing. Okay, that's so you have to remember this Lagrangian. It's not very difficult. It's just half mv square minus q phi plus q a vector dot v vector. Okay, all right. Okay, let's look into another interesting property of this particle in an electromagnetic field, especially a charged particle in an electromagnetic field. Okay, so the important thing is that an electromagnetic field is invariant under a gauge transformation of the scalar and vector potential. Okay, the electromagnetic field. You can show that the electromagnetic field, okay, the E vector is equal to minus del phi, okay, minus dou d minus what was it, dou a vector by dou t, and b vector is equal to del cross a. Okay, so it's easily seen that there are a number of potentials that give you number of combinations of scalar and vector potential which give you exactly the same electric and magnetic field. Okay, the potential themselves are not measurable directly. Okay, the physical quantities are actually the electric and magnetic field. These are the things that we measure. All right, so you can convince yourselves that if you change a vector simultaneously, if you change a vector to a vector plus del vector psi is some function of r vector and t. Okay, and at the same time you change phi to phi minus dou psi by dou t. That will give you exactly the same the same electric field and magnetic field. This is known as a gauge transformation. Okay, now it's easier to see this in the 4 vector form if you are familiar with it. Okay, because the electromagnetic field tensor, it's a second rank antisymmetric tensor. If you remember, it's f mu nu is equal to dou mu a nu minus dou nu a mu, if you remember this. Okay, but it's a good thing to remember these things. It's easier to keep track of these things there. But you must remember that this a vector and phi, okay, as I said, this a vector and phi can be combined into a 4 vector where phi, actually specifically phi by c, is known as the temporal part or the 0th component. Okay, 4 vector has 4 components, a0 and the rest are a vector. Right, so this a vector and phi can be combined. Okay, you can say they transform as a 4 vector together. So the gauge transformation is actually this: a mu goes to a mu minus or plus. Okay, it doesn't matter. All right, this is known as the gauge transformation. This is known as the gauge transformation. If you don't remember the gauge transformation, this is the easiest way to remember. Okay, why is this so? If you check the components of this, we see that. I just want you to keep this in mind. If you check the components, let's write it in component form. The 0th component and a vector, of course there's a c here, goes to, this is phi by c comma a vector minus the components of dou mu. You have to be careful. The components of dou mu are actually 1 by c dou by dou t, okay, comma del vector, minus del vector, actually it's minus. Okay, this is dou mu. These are the components of dou mu. Now, if you are not familiar with this 4 vector notation, don't worry. We'll be discussing these things in detail when we go to relativistic or special theory of relativity. Okay, there's a section on special theory of relativity. Okay, so this is something that I want you to keep in mind. If you don't follow this thing, don't worry. We'll be discussing these things in very good detail when we do special theory of relativity. Okay, and psi. Okay, so if you see that phi by c, I'll just write it down. What we have here, if you take component by component, phi by c goes to phi by c minus 1 by c dou psi by dou t. This psi is sitting here. Okay, which means phi goes to phi minus dou psi by dou t. That's exactly this thing. Okay, and a vector going to a vector, there's a minus here, I forgot. So a vector goes to a vector minus, and minus become plus, plus del psi r. All right. So this you have to remember. Right. Sometimes there was once a question asked, what are the gauge transformations, or what are the transformations of the potential that leaves the electric field and magnetic field invariant? Okay. This question was asked once, and they may give these options. Okay. They may give a vector plus del psi and phi minus dou psi by dt. You have to remember that these transformations have to be done at the same time. Okay. It's a single transformation when you write it in the form of a 4 vector. It's a single transformation. When you write it as a 4 vector, it is this a mu going to a mu plus dou mu psi or minus dou mu psi. It's also a gauge transformation, doesn't matter. Okay. So you have to remember that it's a vector going to a vector plus del vector psi and phi vector going to phi minus dou psi by dou t. Okay. These together, if you change any of the potential, it need not be invariant. All right, the electric and magnetic field need not be invariant. You have to do both this transformation at the same time. Okay, or if you write it in 4 vector notation, it's just one transformation, a mu going to a mu plus or minus dou mu psi. Okay. Now, don't worry if you don't remember this. I just think that this is a good way to remember this thing. Right. So if the question is asked, maybe they'll ask with minus here and plus here, that's also possible. This is also gauge transformation. Maybe they ask minus and minus, then you should know that it's not correct. They may ask plus and plus, and you should also know that that's not the correct gauge transformation. Okay. Here psi is arbitrary but differentiable. Okay. So the question is this, is the problem. What effect does this gauge transformation have on the Lagrangian of a particle moving in the electromagnetic field? Is the motion affected? Okay. The question is the equations of motion affected? Right. So we have to check whether the equation of motion is affected. So we'll try this problem. Okay. So Lagrangian for a particle in an electromagnetic field is this. Now we make this following transformation to this Lagrangian. Okay, and see if the equation of motion is affected. Okay, so you change this phi to phi minus dou psi by dou t, and this a vector to a vector plus del vector psi. Okay, that's exactly what we do here. This Lagrangian in this case changes to, instead of phi, I put phi minus dou psi by dou t here, and instead of a dot v, sorry, instead of a, I put a plus del psi here. Okay, now you just write it down, expand this. This is t minus q phi plus q a dot v. This is the old Lagrangian. This is the old Lagrangian itself, and there's another term here, q multiplied by dou psi by dou t plus v vector del psi. What's this term? This is actually d psi by dt. Am I right? This is actually d psi by dt. We just explained it before some time. If you have some function f of x comma y comma z and t, okay, you can write df by dt always in this form. It's dou f by dou t plus v vector dot del vector f. Okay, that's exactly what we have here. You can convince yourself again by expanding it, and this is actually a total time derivative. You see that the Lagrangian changes only by a total derivative. This is the old Lagrangian, and the change is by a total derivative. Okay, it's a change by a total derivative, and you might have already noticed that the equations of motion do not change when we make this transformation, L going to L plus some d lambda by dt. Okay, so if you change, you have this freedom in finding the Lagrangian. If you have one Lagrangian that gives you the correct equations of motion, then L plus a total derivative will also give you the same equations of motion. Okay, you can check the textbook for a proof, or you might have done this in the class. If not, you try. Okay, so you prove that the equations of motion do not change when you make this particular transformation. I think I mentioned this in the one of the previous classes. If not, I want you to prove this is a homework. Okay, I can give you the solution. I can upload the solution if you like. It involves a few steps and a little bit of careful mathematics. Okay, you have to be very careful, but it's not very difficult to show that L and L plus d lambda by dt, this is a total derivative of some function. Okay, you can actually show that. This is a homework. You can try that. Show that L and L plus d lambda by dt, or d psi by dt if you like. Okay, this gives you exactly the same equations of motion. Okay, you can check this. Okay, we have this freedom. It's called gauge freedom. All right. So a transformed Lagrangian equals the original Lagrangian plus a total time derivative. But we proved in the previous problem. Okay, we didn't do that problem. We can do that. Okay, so you proved in your homework that adding a total derivative to any function to a Lagrangian, any function or a total time derivative of any function to a Lagrangian does not change the equations of motion. So the motion of the particle is unaffected by a gauge transformation. Okay. Now the fact that this electromagnetic field, okay, has this particular symmetry is very important. When you go to particle physics, for example, quantum electrodynamics, this particular symmetry becomes very important. Right? We build up the whole theory based on this particular symmetry. Okay? Just a hint, that's an extra hint for you if you are going to study these things, quantum field theory, quantum electrodynamics, etc. Okay? This is how we introduce forces, all right, by demanding that our system has certain symmetries, all right, and this symmetry is a fundamental symmetry. Okay, we actually a more specialized symmetry than this. This is a more general case, a more special, okay, or more general in a way. Okay, more general. So this is a special kind of symmetry. A more general, the fact that the fact that our system has some sort of symmetry leads to the forces of nature. Okay, that's the basic idea of quantum field theory, but that's just an extra point for you if you are going to do these things later on. Let's just do one more problem before we conclude. Okay, a particle of charge E moves in 3 dimensions in the presence of a uniform magnetic field B is equal to B0 Z hat. Okay, that's a nice magnetic field. It has a component only along the Z direction. And the uniform electric field E equal to E0 x cap. The potential energy is given. I think we should have an R vector there. Okay, the potential energy is U of R vector comma R vector dot is equal to minus E E0 x minus E by C B0 x y dot. All right. Question, find the canonical momenta Px, Py and Pz. Identify all conserved quantities. All right. So we can just write down the Lagrangian in the form T minus U and find the momenta Px, Py and Pz by finding dou L by dou x dot, dou L by dou y dot and dou L by dou z dot. Okay. Now we are also asked to identify all the conserved quantities. Okay. This we can do by looking at cyclic coordinates. We know that the momentum conjugate to cyclic coordinates are conserved. We saw that this is a special case of what we call the Noether theorem. So let's see if it has any symmetry. So before going into that, we compare this with the usual electromagnetic the potential for a particle, the potential energy for a particle in an electromagnetic field. It is minus E phi minus E by C A vector dot V vector. Okay, this C it's a bit messy sometimes. Okay, in the beginning we sometimes we'll put the C equal to 1 or sometimes we'll absorb it inside here. Sometimes it's written explicitly, but don't worry. Okay, so because there's a C here, let's compare it with minus E phi minus E by C A dot V. Okay. So from here we see that this A vector sitting here, the A vector sitting here has to be B0 x y cap. Why? Because we have got only the y component of velocity. Okay, this is actually y component of velocity. This y dot is actually y component of velocity. Okay. The total velocity vector is Vx x cap plus Vy y cap plus Vz z cap. Okay, and the total A vector is A x cap plus A y cap plus A z cap. Am I right? So when you do V dot A, it's being said that when you do V dot A or A dot V, you get x y dot. You get x y dot. Okay, that means that the only component appearing here is Vy. Okay, y dot. So the only component appearing here would be correspondingly Ay. Okay, so we can say that. So because there's only y dot here, we can say that we can write A vector as B0 x y dot. Okay, because if you take a scalar product with, let's say, the velocity vector, okay, Vx x cap plus Vy y cap plus Vz z cap, you see that you'll get this back. Okay, you'll get this Lagrangian back. So by comparing with this, we identify that A vector is equal to B0 x y cap. This means that, see, as I said, this A vector is not a unique thing. You have got a freedom. It's known as gauge freedom or gauge transformation. You can if a set of potentials, if a set of scalar and vector potentials give you the electric and magnetic field, then there's a large number of scalar and vector potential which will give you exactly the same electric and magnetic field, and these are associated by, or these are related, these different potentials are related by what we called as the gauge transformations. Okay, so this is our vector potential, or in another way we can say it in some gauge choice. Okay, this allows us some sort of freedom to choose. There is some choice there, so there is some gauge choice in which a vector is given by b0 x y dot. Now let's come back to the problem. This is our Lagrangian, okay, because it's t minus u, right? This is our Lagrangian here. Canonical moment are dou L by dou x dot equal to mx dot, okay, because there's nothing here. Dou L by dou x dot, this is the only place where x dot appear, okay. Py dou L by dou y dot equal to my dot, and there's y dot here, so you also have e by c b0 x, and px equal to dou L by dou z dot, okay, that's equal to mz dot, okay. Now which are the components of momenta that are that are conserved? Okay, you look at the Lagrangian and see if any x, y or z are missing from this, right? missing from this. We see that x is here, so this means that px cannot be a conserved quantity, right? So we see that, but the Lagrangian is missing y and z, so the corresponding conjugate momenta also will be conserved. Okay, so we say that py is a conserved quantity because y is a cyclic coordinate, and this is momentum. Okay, all right, and pz, because z is a cyclic coordinate, pz is also a conserved quantity. There's one more conserved quantity. You see that there's no t appearing anywhere here. There's no t, time, explicitly appearing anywhere in the Lagrangian, and we have already shown that if the Lagrangian does not explicitly involve time, if the Lagrangian has no explicit dependence on time, then this particular quantity, we have seen it in the last class, then this particular quantity, which we call as the energy, the total energy, is also a conserved quantity. Okay, so you can just do this. We know px, py and pz, so just substitute it all there, and you see that E is equal to half m x dot square plus y dot square plus z dot square minus E0 x. That's another conserved quantity. So we have got three conserved quantities, which are the y component of momentum, the z component of momentum, and the total energy of the system. All right, we say that the total energy of the system is conserved because the Lagrangian does not involve time explicitly. This we had proved in the previous class. So with that, we will conclude today's session, and I'll see you in the next class. Thank you.